Welcome to Ask and Learn.
This question is a mass defect question where we need to figure out the difference in mass between the summed mass of all the protons, neutrons, and electrons that are found in each of these nuclei and subtract that from the actual mass. This will then give us the mass defect. From the mass defect, we can use the Einstein equation in order to calculate the energy associated with the formation of these nuclei. To do this, we need to know the mass of the protons, the neutrons, the electrons, and the nuclei in question. The first one is plutonium-232. The mass defect for an entire mole will be Avogadro's number multiplied by the mass defect for a single nuclei. So we'll take Avogadro's number, 6.022 times 10 to the 23rd, and multiply it by the mass defect of a single nuclei, which will be the actual mass of the plutonium-232 nuclei, which is given to us, minus the summed mass of the protons. There are 94 protons, multiplied by the mass of a single proton, 1.67262 times 10 to the negative 24, plus the mass of the electrons. There are also 94 at 9.10939 times 10 to the negative 28 grams, plus the mass of the number of neutrons. Plutonium has a mass number of 232. We subtract that from its atomic number, and we get the number of neutrons of 138. We multiply that by the mass of a single neutron, 1.67493, times 10 to the 24 grams. This then gives us a mass defect for an entire mole of nuclei that are formed of 1.9073 grams. The negative because mass was lost, or 1.9073 times 10 to the negative 3 kilograms. We need to convert it into kilograms in order to use the Einstein equation. The difference in energy, or the energy that will be released, will be equal to the mass that was lost, delta m, multiplied by the speed of light squared. The mass defect, or the mass that was lost, we calculated as negative 1.9073 times 10 to the negative 3 kilograms. We need to use kilograms with the Einstein equation, multiplied by the speed of light, which needs to be in units of meters per second, 2.9979 times 10 to the 8 meters per second. We then get negative 1.714 times 10 to the 14 joules. This is the amount of joules that would be released upon the formation of a mole of plutonium-232. We'll then do the same thing with protactinium-231. Its mass defect for an entire mole will be Avogadro's number multiplied by the difference in mass of a single protactinium nuclei that is formed, which will be the actual mass of a protactinium nuclei minus the summed mass. Protactinium has an atomic number of 91, so there are 91 protons. Multiply that by the mass of a proton, 1.67262 times 10 to the negative 24, plus the number of electrons, 91 also, multiplied by the mass of an electron, 9.10939 times 10 to the negative 28 grams, multiplied by the number of neutrons, which will be the mass number minus the atomic number, gives us 140 neutrons, multiplied by its mass of 1.67493 times 10 to the negative 24. We then get a mass defect of negative 1.9063 grams, or negative 1.9063 times 10 to the negative 3 kilograms. We then use this kilogram mass with the Einstein equation as the mass defect multiplied by the speed of light squared, in order to get the energy that was released for the formation of a mole of protactinium-231 nuclei, which is negative 1.713 times 10 to the 14 joules